2018 Canadian Open Mathematics Challenge, Part C. At Math Mart, cans of cat food are arranged in an pentagonal pyramid of 15 layers high, with 1 can in the top layer, 5 cans in the second layer, 12 cans in the third layer, 22 cans in the fourth layer, etc., so that the kth layer is a pentagon with k cans on each side. How many cans are on the bottom 15th layer of the pyramid? Okay, so I will definitely need a lot of space. Okay, so in the first layer, they actually tell you that it's 1. And then the second layer, which is n equals 2, it's 5. They're showing you that here. You see, I'll keep that in the view, actually. Probably a good idea to keep it in the view. So n equals 3 is 12. N equals 4 is 22. N equals 5 is 35. So all I'm doing, I'm just counting. So this was 1. This is 5. This is 12. This is 22. And the next one would be 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35. So that's all I'm doing. I'm just counting those. So, and that I wrote it already. So if you keep going like this, this one is 51, if you count it. You should be able to see at least some sort of a pattern. And what I saw is the pattern, which is the difference. The difference between 1 and 5 is 4. The difference between 5 and 12 is 7. This difference is 10. This difference is 13. This difference is 16. So as you can see, the differences are going up by 3 each time. So you can just keep going like this. It won't take us that long. 7, 8, 9, 10, 11, 12, 13, 14, 15. If you just keep going up like this, you can get each of these numbers. So the next one should be 19, and then the next one should be going up by 3 every time, 22, 25, 28, 31, 34, 37, 40, and the last difference is 43. And then you can just fill in these in. This would be 51 plus 19, which is 70, 70 plus 22, which is 92, 92 plus 25, 117, and so on, right? You guys get the point. So 145, 176, 210, 247, 287, and 330. So the answer is 330 because they wanted the 15th row, layer, whatever they call it, 15th layer. Now, you say, well, that's very time consuming. Well, sort of, I guess, right? Is there any faster way? Perhaps. What you can also deduce is that to get each of these numbers, you really were adding 1 plus 4 plus 7 plus 10 plus 13 plus 16, right? And so on, dot, dot, dot. And this is an arithmetic sequence. Arithmetic series. Right? So in an arithmetic series, A is 1. And the common difference in this case is 3. And our n, which is the number of terms, is 15. And the sum, there's a formula. It helps to remember this formula. It's not that hard to remember. It's n over 2 times 2a plus n minus 1 times d. So let's plug in these numbers. We got 15 over 2, 2 times 1, plus 14 times 3. So that's going to be 14 times 3 is 42. 42 plus 2 is 44 times 15 over 2. So that's 15 times 22. And I believe that is 330. So we got the same answer. Whichever way you want to do it is fine, as long as you get the right answer. Part B, the pentagonal pyramid is rearranged into a prism consisting of 15 identical layers. How many cans are on the bottom layer? Okay, so this time what they're saying is that Let's try to get some space here. We've got layer 1, layer 2, layer 3, right? Dot, 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 until we get to layer 15. And all of these layers, they're adding it all up. So we actually got that sum, those sums. Maybe I can just do it over here since we already got it up here. This was layer 1, this was layer 2, layer 3, layer 4, all the way up to layer 15. So we have to add all these guys up. So we have to add the 1 plus 5 plus 12 plus 22 plus 35, right? All of those guys, dot, 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 until we get to 330. So this is essentially layer 1 plus layer 2 plus layer 3 plus layer 4 plus layer 5 plus dot, 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 all the way to get to layer 15. Okay, when you add all those guys up, you can do it manually in a calculator, or if you're not allowed to use calculators, you can just do it manually. It might take a little bit of time, but the bottom line is that it adds up to 1800. Now they're saying in the question that all the layers have the same number of cans this time, because the shape this time is a prism. Yeah, it's not a pyramid anymore, it's a prism. 15 identical layers. So each layer is identical. So the total number of cans, and this is the total number of cans. And since all 15 layers have the same number of cans, we can just take that 1800 and divide by 15 to get 120, and that is how many cans are in each layer. Number of cans in each layer of this prism. Okay. Now we move on to part C. Here we go. C. A triangular prism consists of identical layers, each of which is a shape of a triangle. The number of cans in a triangular layer is one of the triangular numbers, 1, 3, 6, 10, dot, dot, dot. For example, a prism could be composed of the following layers: n equals 1, n equals 2, n equals 3, n equals 4. Prove that a pentagonal pyramid of cans with any number of layers L greater than or equal to 2 can be rearranged without a deficit or leftover into a triangular prism of cans with the same number of layers L. Okay, so let's see here. We are told that layer 1, I'll just do it up here, is 1. Layer 2 is 2. Layer 3 is 3. Layer 4 is 4. Like that in this diagram. But that's just the rows. What we really want to get is the actual number in the total. So when we only have n equals 1, there'll be just 1 can. When we get up to n equals 2, then we have 3, right? Because you have to add up all of them, not just an individual row. When n equals 3, we have 6 cans. When n equals 4, we have this, which is 10, and so on, right? So that's what they mean. So if you keep extrapolating, n equals 5 would be 15, n equals 6 would be 21, and then dot, dot, dot. Just for n, it would be, essentially, it's the sum, 1 plus 2 plus 3, dot, 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 until we get to n. And you guys know that formula. It's n times n plus 1 over 2. And that is a fairly well-known formula, the sum of consecutive integers from 1 to n. Now that is true for a prism, this triangular prism. But they now start talking about the pentagonal pyramid, right? They want you making a comparison. In a pentagonal pyramid, we had previously shown that it's different. It's this kind of scenario here. And we showed that we can basically get that with this formula. So let's talk about that, since we've already done it. Might as well just do it again instead of rehashing it all over it. So we've got that in each layer, we've got a sum, and using that formula, it is, if you remember, n over 2 times 2a plus n minus 1 times d. And if you recall, a was 1 and d was 3. Now I'm going to just do it for n because we are looking at it from the perspective of any n. So the sum would be n over 2 times 1 plus n minus 1 times 3. So that looks like n over 2 times 2 plus 3n minus 3. So that's going to be 3n minus 1 times n over 2. And that is 3n squared minus n over 2. Yeah. So what that means is that in a pentagonal pyramid, each layer has 3n squared minus n over 2 cans, right? And then in a, what is the shape again? Triangular prism. In a triangular prism, so triangular prism, each layer has this guy, n times n plus 1 over 2 cans. So what they want you to figure out, or prove rather, is that a pentagonal pyramid of cans with any number of layers can be rearranged into a triangular prism of cans with the same number of layers. Okay, so that means mathematically we have to equate the two. So we have to somehow show the following. We have to somehow show that if you take the sum of all these guys, so 3k squared minus k over n, over 2, from k going from 1 to n, that's going to be equivalent to this times n, because it's got to have the same number of layers, right? Yeah, same number of layers. Okay, so we have to show that this is equivalent to this. Exactly. So that there's no leftovers, there's no extras. No deficit and no leftover. Okay, I wish they had given us this formula instead of having us to go through all of this, but that's fine. I guess they're making it a little bit challenging. All right, so k equals 1 to n, 3k squared minus k over 2. So I'm just going to concentrate on this part, and hopefully in the end I'll have that part. At least I hope. Okay, so let's break this up. So this is going to be 3k goes from 1 to n of k squared minus, I guess the 1/2 goes up front, of k going from 1 to n of k. Okay. So this is going to be essentially the sum 1 squared plus 2 squared plus 3 squared plus dot 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 all the way up till n squared. And this is 1/2 times 1 plus 2 plus 3 plus dot 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 all the way to n. Okay. All right, so sorry, this should have been 3 over 2, right? Yeah, sorry about that. That's okay. I caught it in time. Okay, well, this one here, this guy, you know that formula. It's n times n plus 1 over 2. This, however, is a little bit lesser known of a formula, but it is very helpful to remember that. That formula is n times n plus 1 times 2n plus 1 all over 6. Okay? All right, so let's do this now. This is going to be, this will cancel with that to give a 2, so this will be 1/4. And that will be n times n plus 1 over times 2n plus 1. This also is a quarter, so it's a good thing I could factor that out, this 2 and the 2. And that's just n times n plus 1. All right. Okay, let's see. Now I've got to do all that stuff in the bracket. I can factor out an n times n plus 1. And when I do, I get 2n plus 1 minus 1. So that's going to be a quarter times n plus 1 times 2n. And then this is going to be, the n will cancel with the 2 will cancel with the 4, so we'll just have a half. And that'll just be n times n plus 1 times n. And I think that's it. And then this can be rearranged. You can put the n out front. N times n plus 1 over 2. Great. I got it exactly like this. So that's essentially what they want you to prove. N layers. This is what this really means is you have n layers with this many cans in each layer, which is essentially what they wanted you to prove. Alice has two boxes, A and B. Initially, box A contains n coins and box B is empty. On each turn, she may either move a coin from box A to box B or remove k coins from box A, where k is the current number of coins in box B. She wins when box A is empty. If initially box A contains 6 coins, show that Alice can win in 4 turns. Okay. So we have box A and box B, and initially we have 6 coins in box A. So we'll make a little table here. We'll put how many she removes from box A, how many are in A and B, and I think that's it, right? And then we have turn 1, turn 2, turn 3, turn 4, turn 5. Let's see. So I only need 4 turns because they wanted me to prove that it can be accomplished in 4. Okay, so let's see. If she removes 1, she can remove a coin. So only 1 coin, or the number of coins that are in box B. But B initially has 0. So her first move is only 1. That's the only thing she can do. If that's the case, after that move, she now has 5 in box A and 1 in box B. Now she can remove either 1 or she can remove the number of coins in box B. But B is also 1. So I guess second move is also only 1. And then she removes it. So this drops down to 4. This now becomes 2. Now she can remove another 1, and this drops down to 3. This now becomes 3. Now we can utilize that rule that you can remove the number of coins that are in box B. Box B has 3 coins, so we can remove 3 coins now. That's why I can put a 3 there. And if that happens, we're now down to 0. And this stays as 3. Yeah. So she wins when box A is empty. So since box A is empty, she's won. Now the key to this question is that, well, at least my opinion is that you got to read it carefully. She may move a coin from box A to box B. So she can remove 1 coin from box A to box B. That means she's transferring to box B, but she is not transferring if she uses this part of the rule, where if she removes k coins from box A, where k is the number of coins in box B, do you notice there's no transfer there? So in this step, we removed the k coins from box A, right? Because k was 3, and removed 3 from box A. But we did not transfer those coins to box B. This didn't become a 6. It became a 3. And that's something that some students may not be able to detect, and therefore you'd never be able to get the right answers for this question. Okay, no problem. I guess that solves part A. Let's keep on going here. Part B. Initially, box A contains 31 coins. Show that Alice cannot win in 10 turns. Okay, so she cannot win in 10 turns. Okay. So same kind of thing. Let's make a little table here. Removes. And then we've got A and B. And then we've got our turns 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And we've got to show that this is not possible if you start with 31 coins. Okay, so initially we start with 31. And then obviously initially it's 0. So let's just see what happens. Yeah, you have to experiment a lot here. So I did, and then I got this pattern. Like if I did one at a time, then I've got 1, 1, 29, 2, 1, 28, 3, 1, 27, 4, 1, 26, 5. And then I implemented that K rule where I remove K coins. So I'm going to remove 5, and this drops down to 21. But remember, this stays 5 because I do not do a transfer if I remove K coins. And that's a key part of the question to remember. Remove another 5. This drops down to 16. This stays at 5. Remove another 5. We're down to 11. Stays at 5. Remove another 5. We're down to 6. This stays at 5. Remove another 5. We're down to 1. This stays at 5. So I came close to getting the 0 coins, but I didn't. I got down to 1, and now I'm stuck. I can't do anything. I can keep going here, but I can't win in 10 moves. I can remove, 1 coin on the next move, but that would be in an 11th turn. They want me to show that what happens in 10 turns. Okay, I said no problem. Let me see if I can keep going here. Let's try another kind of strategy. Same sort of, number of turns, but this time, let's see if I can somehow end up with 0. Okay, so I experimented once again, and this is what I got. So this time I'm going to keep going 1, 1, 1, 1, 1, but one more 1, like that. So what I mean by that is that that's how many I'm going to remove. So I'll just put the removes here. 1, 1, 1. Let me do it in a different color here so it doesn't look as confusing. So we got 1, 1, 1, 1, 1, 1. So by the same principle, this would be 30, 29, 28, 27, 26, 25. And this would be 1, 2, 3, 4, 5, 6. Okay, now I implement the K rule, which I remove K number of coins. This drops down to 19. This remains at 6. Now another 6 I remove. This drops down to 13. It remains 6. Another 6 drops down to 7. This remains 6. Remove another 6. This drops down to 1. This remains 6. So again, I end up with 1. And it's sufficient to show examples like these to show that no matter what scenario you use, you can never get 0 in 10 turns. You can probably get it in less than 10 turns or more than 10 turns, but in 10 turns, you cannot get 0, and therefore you cannot win. Part C, what is the minimum number of turns needed for Alice to win if the box initially contains 2,018 coins? All right, so this time we have 2,018 coins, and this is, again, a lot of experimentation, but this is the way to do it. So we got n is equal to 2018, right? So removes A and B. And initially A is 2018, initially B is 0. Okay, so for the first 38 turns, turn 1, turn 2, ... until 38, you remove 1 coin, ... 1 coin. So this initially becomes 2017, then 2016, and eventually, after removing 38, you get down to 1980. And this is initially 1, then 2, then after 38 coins, this will be 38. So that's the first part. Then you use the K rule, which is you remove 38. So I'll just put that in here, the K rule. So on the 39th turn, you use the K rule, which means you remove 38, which is how many are in box B. That drops this down to 1942. And this remains at 38, because remember, when you use the K rule, you are not doing a transfer. Then you go back to the 111 scenario, like here, 7 times, 40, 41, all the way till 46. And so I got 1, 1, all the way down to 1. And so this goes from 1942 to 1941, 1940, all the way down to 1935. And this, of course, would become 39. This would be 40, all the way till 45. And then you have to use the K rule. The K rule is going to be used several times from 47 till 48, and then keeping on going until 89. So you're using the K rule here up once, but here the K rule is going to be used 43 times. So each time you're going to be removing 45. So 45, that would make this 1890. It stays at 45, remember, because you don't make a transfer. 45 again, 1845. This remains at 45. And then you just keep doing that until you get to here. It'll be down to 45. You have to remove 45, and it'll bring it down to 0. So the 88th one, there will be 45 left here. And yeah, so that means the total is 89, and this is the minimum number, the minimum number of turns needed for Alice to win. Consider a convex quadrilateral ABCD. Let rays BA and CD intersect at E. Rays DA and CB intersect at F, and the diagonals AC and BD intersect at G. It is given that the triangles DBF and DBE have the same area. Prove that EF and BD are parallel. So here is a nice diagram that illustrates exactly what they're talking about in the question. Now, they're telling me that the triangles DBF and DBE have the same area. So DBF, and DBE, so DBE, they have the same area. So that means the heights from E and F to line DB are equal in length. So, for example, if we were to draw a line that kind of extends DB like that, and then we were to draw two heights one from E down to DB that makes it perpendicular, so like this, where that's perpendicular, and one more that from F down to DB that's perpendicular, approximately like this, right? Yeah. Then we can also draw another line that connects sort of E and F, and that will look like this, approximately like that. And now, hopefully, you can see that since these are perpendicular lines, that's a right angle, that's a right angle. And the reason they're equal in length is, look at the area. DBF, the area, and DBE, they're saying are equal. Now, what is the area of DBF? 1/2 base times height. Well, we can use DB as the base, and the height, we can use this one, this H. Well, let's call this X, and let's call this Y. So EX, right? This one is 1/2 base times height. Again, you use DB as the base, and the height you use FY. So that means that EX is equal to FY. So that means this is the same as that in terms of its length. So that's how I got that. And if that's the case, then EF and DB are parallel. Because if they're the same length, then that means this is a right angle, and this is a right angle. So therefore, you can conclude that EF and DB are indeed parallel. Okay, so that takes care of part A. Prove that G is the midpoint of BD. Okay, so a lot of steps in this one. This diagram will definitely help us. BDEF, if you look at that, is a trapezoid. And we have to now look at this diagram. Now, A is the intersection of the diagonals, and C is the intersection of the legs. So, as before, DBF, that triangle, is equal to triangle DBE, right? Those have equal areas. So, since those have equal areas, we can also conclude that ADE is equal to ABF. ADE and ABF. Because each of those basically contains DBF and DBE both contain this triangle. So if you subtract it from both, what you get left with must be equal. All right, so now we want to draw altitudes AJ from here to here, which is already drawn, and AH, like that. So we got altitudes AJ and AH. And then since ADE is equal to ABF, that essentially means 1/2 base times height. So for ADE, we can use ED as the base, and the height, we can use the AH. And on ABF, we can use BF as the base, and as the height, we can use AJ. Correct? And then when we rearrange this, we get basically ED over BF is AJ over AH. Okay, so that's the first part of this. Now, we previously showed that EF was parallel to DB. And since that is true, we can deduce that the triangle DBC, that's that guy there, is similar to triangle EFC, the big one, that whole thing. All right. So now we've got to use similar triangles to get some sort of a relationship. So I can conclude that DC over EC is the same as BC over the whole thing FC. And therefore DC over EC, which is just DC plus ED, is the same as BC over FC, but FC is just FB plus BC. Now, therefore, I can flip this and just get ED plus DC over DC. And this is FB plus BC over BC. Now, if I break this up, this becomes ED over DC plus 1. And this becomes FB over BC plus 1. And therefore, finally, we can conclude that ED over DC is equal to FB over BC. All right. Now, we had previously concluded that ED over BF is this, but we have to manipulate this just a little bit. We have to put ED over FB. FB is the same as BF, so I'll just write BF is DC over BC, like that. Now, we had previously proven that ED over BF is AJ over AH, so we can just put AJ over AH right here. They're all equal. Right? So this is all one statement that makes sense. So now what I'm going to do is just look at these two guys, bring it up here, that because of that, we can cross multiply and say that AJ times BC is the same as DC times AH. And if that's the case, then that means that AJ times BC, if we put a half in front of it, you're essentially calculating the areas of two triangles. Which triangle? Well, this one, AJ times BC, is this triangle right here, triangle ABC. And this one here, DC times AH, that's this triangle right here, ADC. So that proves that those two triangles are equal. Okay, so now, finally, we will get to a conclusion. Now we have, let's just stick to this diagram here. I think I can squeeze it all in. That we have this M and N. Here's M and here's N. And they are basically the foots of the perpendiculars. So we have a perpendicular drawn from B to this line AC, and its foot is M. And then we have a perpendicular drawn from D to that same line AC, and its foot is N. So the diagram explains it. Now we have concluded over here that triangle ABC is equal to triangle EDC in terms of its area. So that means that 1/2 ABC, if we use this as a height, which is going to be BM, and this now as a base, we can write it as follows. We can write 1/2 base times height. And then for ADC, if we have this triangle, we can use this again as a base, which is AC, and this as the height, which is DN. So 1/2 AC times DN. So therefore, BM is equal to DN. And since we know that BM is parallel to DN, right? Because they're both hitting that at right angles, as you can see there and there, we can conclude that the triangles GBM and triangles GDN, GBM is this guy, GBM, that small one, and GDN, the small one, are congruent. And since they are congruent, we can conclude that DG is equal to GB. And that therefore proves that G is the midpoint of the line BD. Part C, given that the area of triangle ABD is 4 and that the area of triangle CBD is 6, compute the area of triangle EFG. So ABD, they're saying, is equal to 4, and CBD, they're saying, is 6, and they want me to find EFG. Okay, the area of that triangle. Okay, so a lot of this will be sort of repeating parts A and B. And if you recall, we had figured out that ABC was equal to ACD. Now ACD, if you look at it, the diagram is really just ABD plus CBD, right? Because ACD is right here, and that's ABD plus CBD divided by 1/2. So I hope you can see that from the diagram. So since we are given these dimensions, we can just sub them in. So this will be ABD is 4 and CBD is 6. So this looks like that will be 5. Okay, so that's something we will use. Now we can use a sort of ratio that ADE, which is right here, ADE, this triangle, over ABD, which is ABD, this guy. Let's see what we get. Well, ADE, I don't know the actual value, but ABD I know is 4. But this part is what? 1/2 base times height. So 1/2 ADE. So I can use AE as the, I'm going to use that as the base this time. And I'm going to use a height that's different. So let me draw in that height. So I'm going to use a height drawn to D. So for example, something like this. Well, that where that red line is that perpendicular height. ABD, use something similar, 1/2 base times height. For ABD, I will use AB as the base, and then it has the same height. You can use the same height, interestingly. And therefore, this just breaks down into just AE over AB. Okay? Now, we can get a very similar relationship if we compare two other triangles, and that is AEC and ABC. So where's AEC, first of all? AEC is this big one, AEC. And ABC is this one right here. So in a very similar way, I'm going to draw two heights, and this time they're going to be drawn to C. So that big one I could just call big H. So that will be a perpendicular right there. So we're going to AEC, it'll be 1/2 base. I'll use AE as the base times height. And then for ABC, 1/2 base, I'll use AB as the base times the height, like that. So this just breaks down to AE over AB, which is exactly what we have here. Okay, now this needs to be expanded a little bit more. AEC is actually ADE plus ADC or ACD, and then that just stays as ABC. Now ADE plus ACD, well, that's the same as ADE plus ABC, right? Because this ABC is the same as ACD, as we had previously stated. ABC, like that. And this is equal to ADE plus ABC, which we had calculated as 5. So plus 5, and ABC, again, is 5. So that means that this is equal to this, and this is equal to that. So we can equate them. ADE over 4 is the equivalent of ADE plus 5 over 5. And now we can solve. So we cross multiply, and you get 5 ADE is equal to 4 ADE plus 20, and therefore ADE is equal to 20. All right, we still have to figure out this EFG though. So we gotta have a couple more steps here. EFG is equal to EFD, and that is essentially equal to FDC times DE over DC, which would be the same as FDC times ADE over ADC, and therefore that would be ADE plus 10 times ADE over 5, since ADC is 5, and therefore that looks like 20 plus 10 times 10 over 5, and that is, 20 over 5, and that is 4 times 30, which is 120. So the EFG, the area, is 120. Given a positive integer n, Matt writes n in decimal on a blackboard without writing any of the leading zeros. Every minute he takes 2 consecutive digits, erases them, and replaces them with the last digit of their product. Any leading zeros created this way are also erased. Repeats this process for as long as he likes. We call the positive integer m obtainable from n if, starting from n, there is a finite sequence of moves that Matt can make to produce the number m. For example, 10 is obtainable from 251023 via this process. Show that 2008 is obtainable from 25677777899. Okay, so first let's explain this. They took 251023. Then they take this, and with that, you do what is exactly defined in the question. That you replace them with the last digit of their product. So what is the product of 2 times 3? 6. What's the last digit of 6? Well, 6. The last digit of 6 is just 6. So you just replace 2510. You add the 6 there. You replace it. And then what they've done is they've done this. They've taken 2 times 5 now, which is 10, and replace it with the last digit. Now, if you replace it with the last digit, it would be 0. But then they have this rule that any leading zeros are erased. Okay, so really what that means is you're just writing 106. Then they take those 2, which would be 0 times 6, which is 0. And therefore, you replace that 06, which is 0. So that's how you get 10 from this. So they want you to show that from this, you can get a 2018. Okay, let's see if we can do that. All right, so we got 2, 5, 6, 7, 7, 7, 7, 8, 9, 9. Okay. First, let's get rid of that. So we have 9 times 9, which is 81, and the units digit, last digit, units digit, same thing, is 1. So this becomes 2, 5, 6, 7, 7, 7, 7, 8, but then you now just put the 1 there. Okay. Now let's do the same thing with those two. So 8 times 1 is 8, the units digit is 8. So this becomes 2, 5, 6, 7, 7, 7, 7, 8. Now let's do it with those two 7s. 7 times 7 is 49. The units digit there is 9. So you'd put 2, 5, 6, 7, 7. You'd put a 9 in its place. And then don't forget that 8. And then now, let's see, which one do you want? Let's get rid of these 7s. So then again, 7 times 7 is 49. The units digit, last digit is 9. So that would become 2, 5, 6, 9. And don't forget the 9 and the 8. Then let's get rid of those guys. 9 times 9 is 81. The last digit is 1. And therefore, this would become 2, 5, 6, 1, 8. Okay, so we already got the 2 and the 0, the 2 and the 1 and the 8 from the 2018, so we're pretty close here. So naturally, I'm going to get rid of these guys. 5 times 6 is 30, and the last digit is 0, so this becomes 2018. And there we go. We have obtained 2018 from that number, which is what they wanted us to show.